So good afternoon, I'm Kevin, and my project is modeling the electrostatics of junctions. So I'm going to give you a quick preview of what I've been working on for the past 4 weeks in Professor Pei Dongyang's group in the chemistry department. So let's take a look at some background about what I'm talking about. This is a semiconductor junction. So on the left side we have p-type silicon, and on the right side we have n-type silicon. And because there are more electrons in the n-type silicon, some of the electrons, when the two materials touch, will move across the junction into the p-type material. So then we'll have this area in the middle called the depletion region. And because all of the electrons have gone to find electron holes on the other side, there are very few electrons and very few holes in this region. So actually across this region we can measure what's called the built-in potential. And if we look at this diagram, this is a band diagram. So as Rio explained this morning, the top one is the conduction band, the dotted one in the middle is the Fermi level, and the bottom one is the valence band. So in the conduction band, electrons are free to move throughout the solid, but in the valence band, they're sort of attached to the atoms that they belong to. And the bent part in the middle is because when the two materials touch, the electrons flow across the junction, and the Fermi levels in the material, which were different before, become equalized. So the conduction band and the valence band have to do some bending, some band bending, in order to meet up with each other. And the bent part of the band corresponds to the depletion region. So again, a built-in potential exists at the boundary between two materials. And this is the operating principle behind solar cells. So solar cells have junctions between two materials like the one that we just saw, and when light energy hits the junction, it kicks some electrons into the conduction band where they are free to flow around, and then these electrons can be sent through an external circuit to do some useful work for us. So here are some materials that have been investigated fairly thoroughly for their applications in solar energy. But there might be some other ones that we want to look at in the future, and there might be a lot of them. So how do we figure out which ones are interesting to us, which ones actually have potential for solar energy applications, without fabricating tons and tons of devices for each test material? Well, that's where my project comes in. My project was to take the band diagram and plot it in MATLAB. And MATLAB is a programming language for doing math on the computer and visualizing the results. So I wrote Plot Junctions, which is software that does exactly that. Plot Junctions is written in 950 lines of MATLAB code under the hood. There's a lot of math going on here, and that's what I'll get into. But if we were to do this by hand, we would need 5 parameters for each material. First, we would need the electron affinity, which is the energy it takes to remove an electron from the conduction band to the vacuum energy, which is a position immediately outside of the atom. Next, we want the band gap, which is the distance between the energy difference between the conduction band and the valence band, which there are no electrons there because there are no electrons there. Next, we want carrier concentration, which is the number of the concentration of carriers, which are either electrons or electron holes. And this is expressed in a density, so carriers per unit volume. We also want the effective mass, which is like mass, but it also takes into account the effects of the crystal on the electrons or electron holes as they move through the material. And finally, we want the relative dielectric constant, which describes how the material responds to an electric field. So in order to plot the bands, first we need to have something to reference to. And in this program, everything is referenced to the vacuum energy. So from the vacuum energy, we take the electron affinity, and we just do some subtraction, and we get the conduction band. And then we take the band gap, and we do some more subtraction, and we get the valence band. So this is looking sort of like what we saw from the textbook, from the scan from the textbook earlier, but we're missing the Fermi level. And so to calculate the Fermi level, it's a little bit more involved. We have a big scary equation here, and this is calculating the density of states from the effective mass and Planck's constant. And so we take the density of states and we put it into the Fermi level equation along with the conduction band and the valence band, and this gives us the level of the Fermi level. So that's how you would do it by hand. In plot junctions, you just need to provide these material parameters, or because I've gone through some research papers and looked at people's experimental data, Plot Junctions has a materials library. So it already knows about a lot of materials, and if you want, it can just import them into the boxes for you, so you don't have to fill them out yourself. And if you really know what you're doing, you can just enter these values in yourself. So we would import these materials, and we would press the plot button, and we would get this diagram of the two band structures before the materials are touching. So we see the green line at the top, and that's the conduction band, and the red dotted line in the middle is the Fermi level, and the blue line at the bottom is the valence band. So notice that the Fermi levels are at different places in the chart right now. That's because the materials have not touched yet, so the electrons don't have the opportunity to move across the junction and balance out the Fermi levels. And the act of balancing out the Fermi levels when the electrons move is called equilibration. And that's the next step in the calculations. So first we find the difference in Fermi levels. We take the material with the higher Fermi level and move all of its bands downward so that the Fermi levels are aligned. Next we would calculate the voltage drop on both sides of the junction. And we would use that to calculate the width of the depletion region, which again is the area with no or little to no carriers. And finally, we calculate the potential curve, which is the band bending that we saw earlier. So this is what the final figure will look like. And so again, we have the conduction band, we have the Fermi levels, which are now at the same Y level, and then we have the valence band at the bottom. So also in the bottom left of the figure, Plot Junctions has gone ahead and calculated the open circuit voltage, which is the voltage that you would measure across this junction if there were no current. And this is the maximum theoretical voltage that you might be able to get if you're building a device like a solar cell. So we're going to come back to this in a later slide. So applications of this program. Here's a nanowire. The inside of it is cadmium sulfide, and the outside of it is copper sulfide. So there's actually, it's a radial structure, and it has a core and a shell. So you'll notice a bunch of green boxes, and in each one of the green box, the wire has been coated with a thin layer of copper sulfide. And so the leads at the bottom connect to the copper sulfide on the outside, and the leads on the top connect to the cadmium sulfide core. So in this way, we can use these leads to measure the electrical properties of the junction. So here's a wider shot, and again we see the nanowires, and we also see that the fork-looking things are connected to pads, which we can then connect to electrodes to measure the electrical properties of the junction. And that's exactly what we did. So on the bottom we have the voltage that was applied to the junction, and on the y-axis we have the current that was measured when there was light falling on this junction. So the open circuit voltage is where the current is 0. So if we draw a line down, we can get the voltage, which experimentally it was 0.603, and from the Plot Junctions program, the theoretical maximum was 0.609. So this is a sort of sanity check for the program to show that it's not only giving numbers in the correct order of magnitude, but also numbers that are at least greater than the results we received experimentally, which means that the math is probably correct. So to summarize, I developed an application that plots band diagrams from material parameters that can be entered into the application, and these band diagrams can predict future materials properties if we were to make solar cells out of them, or they can be used to understand current materials better. So for example, if we know that something works experimentally, we can use this to figure out what's actually going on behind the scenes. In the future, I'd also like to expand this program. I'd like to support metals and liquids. I would like to support radial geometries. So just like the nanowire that we saw, instead of a linear band diagram, I would like to be able to plot what the band diagram looks like when there's a core and a shell. I'd like to plot multiple junctions at the same time. So in this case, we saw a P-type material and an N-type material, but I would also like to plot things like a P-type material, an N-type material, and then another P-type material. I'd like to expand the material library, so it's always nice to have more materials so that users can do less work and get more done. And finally, I'd like scriptable pairing of materials in the library. So what this means is, for every material in the library, we can take it and match it up with all the other materials and make junctions out of them. And if we save the open circuit voltage and then sort it by the open circuit voltage, we essentially have a hit list of the materials that we want to try next. So that's my project, and I'd like to thank Sarah and Anna, who are my wonderful mentors, for their continuous help and their patient explanations of all my questions. I'd also like to thank Aaron, Avi, Professor Chen Hasnai, and Professor Yablanovich for creating and sponsoring the SHARP program. And finally, I'd like to thank Dr. Peidong Yang for use of his lab space and his computing resources. So that's my presentation. Are there any questions? Yes.
For your pictures of the nanowires that you were showing, how are you able to see them under a light microscope?
So is it, let me see if I can find that slide. Are you talking about this one?
Yeah.
So the nanowires are about 200 to 300 nanometers wide, which are actually too small to resolve in an optical microscope like this one. But actually the nanowires sort of interfere with the light in the microscope, so we can see the effects of the nanowire on the light, but we're not actually looking at the nanowire here. Trevor?
Why does your graph that you plotted from your data look different than the textbook? Because the textbook is like moving right down and there's kind of like a sudden drop.
So let me go to that slide. This one?
Yeah.
So with copper sulfide and cadmium sulfide, the cadmium has a very low carrier concentration. So what happens is it doesn't have a lot of electrons per unit volume. So it takes a lot more distance to get the same number of electrons when we compare it to the copper sulfide, which is very, very dense. So it doesn't take a lot of distance. And actually, the two numbers at the top are the depletion widths on both sides of the junction, and the one on the side of the copper sulfide is not 0 nanometers, it's just too small, and it got rounded away.
I have a question.
Yeah.
How would you expand this to metals?
So a metal basically acts like a very, very highly doped N-type semiconductor. So I'm not sure, I took a look in the textbook, but I didn't really read it. But I think that it would just be different numbers. Yes?
So how do you know it's correct?
Well, we don't know that it's correct because the actual device that we're testing with is experimental, so it's not like it's in production or anything. But we know that it's in the correct order of magnitude, and we know that these equations have been used by other people in the past, so we have a reasonably good idea.